Okay, in this video, we are going to look at some sets and determine if they're a vector space or not. So our first testing for vector space here is a set of all 4x6 matrices with the standard operations. So we know this is a vector space because we know from the summary of important vector spaces and the examples we saw that the set of all m by n matrices are vector spaces. And we saw an example previously here. So we showed that the vector space of all 2x3 real matrices is a vector space with the standard operations. So we know if we add up the matrices, we get still, in this case, a 2x3 matrix. And if we multiply a scalar through, we still get a 2x3 matrix. So the same reasoning holds for a 4x6 set of matrices. So you can verify if you want to check. Let's see, 4 rows and 6 columns. So you'd have A1, A2, A3, well, A11, A12, A13, A14, A15, A16. You could see this is going to take a bit. But anyway, you could show all the way through, 4 rows. I'll put some dots in here. All the way through element A46, plus the same thing for a matrix B, that B11 all the way through B46. Same idea. You could show, okay, that's still going to be a 4x6 matrix when we add it up, and the same thing if you multiply through by a constant. So we conclude that, yes, this is a vector space, the set of all 4x6 matrices. All right, let's look now at whether the set of all third-degree polynomials with the standard operations of vector space. So the problem is they're just saying the set of all third-degree polynomials. They're not saying third degrees or less. So we can show the set is not closed under addition. So for example, I can pick negative 2x cubed plus 4x squared, and then add that to positive 2x cubed plus 2x, and my x cubed third degrees there cancel out, so I'm left with 4x squared plus 2x, which is not a third degree polynomial. So we would have to have this say third degree polynomials or less to be a vector space. So this is not a vector space. So we call this a set, but we don't get to call it a vector space. All right, so now here's the set of the ordered pair x and y, where x is positive, has to be greater than 0, and y can be any real number. So this is not going to be closed under scalar multiplication. It would be closed under addition if you checked it, because a positive plus a positive is going to stay positive, and a real number plus a real number is going to stay a real number. But we can say this set is not closed under scalar multiplication. So for example, if I do a negative scalar multiplied by, say, the ordered pair 3, 2, then I get -3 and -2, which is not in the set. So I can say this is not a vector space. All right, now let's look at the ordered pair XX, where X is a real number. So we will check all 10 vector space axioms. So let's go through those. So I'm going to call my points. Let's see, I'll do XX and YY. So X plus Y as vectors is going to be XX plus YY. So that's going to be component-wise X plus Y and X plus Y. Well, that's still in the set, right? These are still identical components, and they're both still real numbers. So it's closed under addition. Let's check the commutative property. So if I do, I already did X plus Y. Now if I do vector Y plus vector X, then that's going to be YY plus XX. So that's Y plus X and Y plus X. But we know by the properties of real numbers, you can add in any order for these components. So property 2 is satisfied. All right, now we have to check property 3. So I got to check X plus Y plus, I guess I'll have to use Z here. And so that's going to be, if we fast forward through our steps, that's going to be X plus, and then we know from our work above, this will be Y plus Z and Y plus C, the components. And then we know this will be X plus Y plus Z and X plus Y plus Z. And then we know through properties of real numbers that we could say, well, this is just X plus Y plus Z here, Z ordered pair. And then that's just equal to vector X plus vector Y, or plus is vector Z. All right, so we've shown that property 3, the associativity property, holds. So now the fourth property of vector spaces is the additive identity. So we have to show that there's a 0 vector. Well, the 0 vector is just 0, 0. That's easy. So vector X plus the 0 vector is just going to be XX plus 0, 0. So you get X plus 0 and X plus 0, which is just XX again. So there's your additive identity. And then the additive inverse, because we're in the real numbers, X is a real number, so our additive inverse is going to be just negative X. So if you've got XX plus negative X, which is still part of the real numbers, then you get X minus X and X minus X. So you get the 0 vector here, and you've got an additive inverse. You could say if you want that this equals the 0 vector. All right, now we have to check the 5 properties associated with scalar multiplication. So first we have to check that if you multiply by a scalar, this is property 6, that you are still in your set. So we know this is going to be CX times CX, which is still in the set because these are still real numbers. and they're still identical. If you want to, you could say this is in the set. How did we name our set? XX, such that X is a real number. So that's a long list. I got to write it like this. It's still in the ordered pair XX, such that X is a real number. Okay, property 7 is a distributive property. So we are going to have C times, we'll say X plus Y here. So then this is going to be C times, we know from earlier, this is X plus Y when we add those vectors. And then we know from scalar multiplication definition that this is going to be C times X plus Y and C times X plus Y. And then because these are real numbers, we know the distributive property holds. So this is CX plus CY in both components. And then we know we can say, well, that's just C times the X vector plus C times the Y vector. So property 7, the distributive property for scalars, holds. And now we have to check the distributive property with adding scalars and then multiplying. So we have to check C plus D multiplied by vector X. So this is going to be C plus D times X in the first component and C plus D times X in the second component. And then we know by properties of real numbers that this is going to be CX plus DX, because C, D, and X are all real numbers. And the same thing here, CX plus DX. And so then we know, well, this is just able to be C times X plus D times X. So property 8, the distributive property under adding scalars and then multiplying through holds. Now we got to check the associative property. So you can see to verify something is a vector space, if it's not something we've already established in the examples given, we've got to go through and check all 10 of these steps. So to check property 9 or axiom 9, C times D times, I'm calling it X, not U here, where X is my vector. I'm going to say this is C times, and I know D times X is going to be dx dx. See, I don't need double parentheses here. Then now when I push C through, it's going to be CDX, CDX in each element. And then I know I could say, oh, well, that's just CD times XX, which is just CD times a vector X. So I showed the associative property for scalar multiplication. And then the last thing to check is the scalar identity. Well, we know 1 is the scalar identity. So 1 times XX is just 1x, which is just XX. Okay, so we have proven all 10 axioms for vector space. So we can go back and say that this set of the ordered pairs XX, where the pairs are, the X value is a real number, so the same number in both places in the pair, is a vector space. So it meets all 10 axioms. So in some of the group discussion problems, I'll have you check to see if spaces or sets are vector spaces or not. So you'll check the axioms and see if you can find a contradiction to show that set is not a vector space, or you'll verify that all 10 axioms hold.